In this video, we'll start addressing the content of our next unit called area. It's all something that you've seen before previously, perhaps in your middle school days, but we're going to formalize it. And I like to start the area unit with a more philosophical discussion about what area is, as opposed to the formal formulas. So in order for us to do that, we first need to establish some vocabulary and some undefined terms. The first term is what a region is, just because in order to address what area is, we have to talk about what it's a property of. Area is a property of a region, that a closed or bound portion of a plane is a region. Consider this example here that's shown on the page, that I have some plane M, that's just a plane, it's infinitely long, and I have some bounded region R, some region R, and I can divide that into two different pieces. The exterior of the interior of the plane. That's the interior region of that bounded portion, and the exterior would be the stuff on the outside of the boundary, where the boundary is that black line that's drawn around the interior of the region. Area cannot be defined in the same way that we've defined many of our other terms this unit. In fact, when Euclid talked about area, he had this struggle of defining what area was. He called it content instead of area, but he rather just agreed that maybe it's something that we can't formally define, but we can think of in terms of describing it. And what it is there a way to quantify the amount of space inside a region, on the interior of the region? That's exactly what an area is. It's quantifying, it's putting a number to the amount of space inside a particular region. We have some postulates that we can use to address some of the properties that we'll see with area. The first one is called the uniqueness of the area. And what it says is that every bounded region has a unique number, alpha, called its area, which, by the way, that is the symbol that we will use to express area, is alpha, rather than a capital A, which is often seen in your middle school days. What this says is that every figure, every region has one number called its area, that it's not possible for instance, this shaded region right here, it's not possible that has an area of 55, for instance, and it also has an area of 32. That would contradict the uniqueness of the area postulate, that only one number can be assigned to any given figure called its area. Now, if that figure changes, the area changes with it, just because the amount of space inside the region changes. It also gives us a way to compare different regions. So for instance, let's say this area is 32. We can fairly easily see, and this one's 55, we can fairly easily see that one has a larger area than the other one, and that's more represented in their diagrams, because in the left-hand picture, this one right here, more space is taken up by the interior of that region than is by this second one. The second postulate is the area addition postulate. And what it says is the area of a bounded region is equal to the sum of the areas of its non-overlapping parts. And that's something that is intuitive to us, but it needs a postulate in order to establish it. All that says is that the area of this entire figure here, this entire figure, is equal to the area of this figure plus the area of that figure. And the big piece here is that it's the non-overlapping parts. If the parts overlapped, we'd have to worry about an overlap of the area formulas, but it turns out that's not the case here. The way that we would represent the area addition postulate in terms of this figure is the area of the entire thing, the area of figure EABCD, that's the entire polygon, is equal to the area of the quadrilateral EABD plus the area of the triangle, CBD. So as we're told in this information over here, if the area of ABDE, that's this left side, is 14, and the area of the right side, that triangle, is 6, then the area of EABCD is the 14 plus the 6, which is 20, that I could characterize that area BCD as being 20 because I had the non-overlapping parts. The next postulate that we can address in the area postulates is this notion of equivalence. But before we get to the particular postulate, I want to define what equivalence is for you. That two regions are equivalent if and only if they have the same area. That, for instance, this region that I'm outlining, the area of this whole rectangle here, DEFG, is 135.54 centimeters squared, and the area of this whole rectangle, HIJD, is 135.54 centimeters. That since they have equal areas, that their areas are equal to each other, I can then say that quadrilateral DEFG is equivalent to quadrilateral HIJD. What we would use this for is to say that postulate 3, that the third area postulates would tell us that if two figures are congruent, then they have to have equal areas. If I can establish, for instance, that I have two different triangles in separate locations in space, but let's say that I know that they have vertex angles that are congruent, and they are both isosceles triangles, and those sides are congruent. I can then say that whatever the area of this triangle is, and whatever the area of that triangle is, they have to be equal to each other. That if I know that I can establish these triangles as congruent, then they have to have areas that are equal to each other. And that goes for any figures, not just triangles. If I can show that two squares are congruent, then they have to have equal areas. The thing I'd like to address here, though, is that it doesn't necessarily go backwards. Just because you know that the area of two different figures is equal does not mean that the figures are congruent. And I can give you an example of that once we address the rectangle area postulate, which is next. But the idea would be that if you know that all the side lengths are not congruent and all the angle measures are not congruent, then you can't establish that the two figures are equal in area. The last thing is the rectangle area postulate, and this is really where we start our area formulas, that the area of a rectangle is equal to the product of two consecutive sides. You may have formally seen this some other time as base times height or length times width. We'll try and stay away from some of that vocabulary in our geometry studies. More formally, I think for a rectangle, that the area of a rectangle, we can more say is generally one of the bases times the corresponding altitude. And I like to say altitude as opposed to height because it tells us from our definition that it has to be perpendicular. In this particular rectangle, for instance, the area of ABCD, I can pick any two consecutive sides, that's sides that are next to each other, multiply them together and I get the area. For instance, I'll choose AB and BC. That the area could be AB times BC, or it could be BC times DC, or it could be any other pairs of consecutive sides. Where might we use this? Well, let's do some examples. Given that AB is 8 and BC is 12, find the area of rectangle ABCD. Since it is a rectangle, oh, I guess I should have said that, but it is a rectangle, I can state that the area is given by 8 times 12 because those are consecutive sides, which is 96. And unless I give you a particular unit, you're not expected to put a unit there. This is supposed to be a rectangle, even though I didn't state it. Number two, given that TREC is a rectangle, that's this entire giant rectangle here, and RT, 10 square root of 3, and RC is 26 square root of 3, find the area of TREC. We're trying to find the area of the rectangle. I'll jump into this immediately and say that we can't just multiply these two numbers and get the area, because what was important is that we need some consecutive sides. Like we have RT, now we either need to figure out TC or we need to figure out RE. But since it's a rectangle, those are two congruent to each other. It doesn't matter which one we figure out. I'm going to pick TC and I'm going to call it X, because since I know this is a rectangle and all rectangles have right angles, I can use the Pythagorean theorem to figure out the value of X. Setting up the Pythagorean theorem, 10 square root of 3 squared plus X squared is equal to 26 square root of 3 squared. Well, 10 square root of 3 squared is 300 plus X squared is equal to 26 square root of 3 squared would be, let me get out my handy dandy calculator. Let's see. Calculator's doing its thing again. 26 squared, 2028. And solving for X squared, that would be 2028 minus 300, 1728. So then finally, if we want to find X there, it's the square root of 1728. In this unit, it will be sufficient for you to provide a decimal approximation so long as you show your work. I want you to show your work throughout the process so that I know you're doing exactly what you're supposed to do. So the square root of 1728 is approximately 41.6. So the area of TREC is going to be this base, 10 square root of 3, times this, this other consecutive side to it, 41.6. And that's approximately equal to 10 square root of 3, approximately equal to 720. But the area would be 720. Just pay attention to what the given information is. The last piece of information that I want to share with you is that this is just where we're starting the unit, with these philosophical underpinnings of what area is and with the rectangle area. Throughout this unit, we'll just go through one by one each of the figures that you might see and how you might find the area of them. We'll go ahead and avoid proofs in this unit too, so feel free to just learn the formulas and work through the problems as you see them.